Hello everyone. I think we will start a little revision of yesterday's class, and I had we were discussing about the instrumentation in yesterday's class, and I had told you that grating dispersive, filter dispersive, Fourier transform IR in spectrometers are the currently in vogue, but most of them contain the components. One is optical source, another is the optical system. One is optical system, another is the source, sample compartment, detector and electronics. These are common to all. And then I had shown you this slide. We had given I had given you an introduction to Fourier transform instrument, and I had shown you a couple of pictures about the Fourier transform, and then prism grating, grating systems, etc. These are dispersive instruments, and then I had given you the range, and then grating blazing I had talked a little bit about it, and then I had shown you this picture. This is the FTIR instrument optics, and it contained a source and then beam splitter, moving mirror and a fixed mirror, and sample and detector. I had shown you this figure of the actual optical system existing in an instrument. Okay. And then the non-interferometric IR spectroscopy, I had shown you this picture which contained grating as a dispersive element. And then the IR radiation about passing through a Michelson interferometer, we had continued our discussion, and then I had showed you the advantages of FTIR. That is, only one moving part is involved and things like that. One is near absolute frequency accuracy, this is one more advantage. Another is signal to noise ratio, that is a Felget's advantage, and then there are other advantages which I had listed here. And then I had explained to you how the IR FTIR functions, the theoretical basis. Now then I had told you that moving mirror keeps on repeating the movement only here, which will represent a 1 degree lambda by 4 for each wavelength, which will give you a cosine signal. And when all the signals are sampled simultaneously, I get a figure like this. This is known as interferogram. This I had not shown you yesterday. So, I had shown you this is the interferogram of the total IR radiation imposed on the sample simultaneously. So, because all the frequencies are simultaneously measured, the signal to noise ratio will be very less. So, this interferogram, when it is applied to the spectrum, that is when we do this de Fourier transformation, what we get is something like this. It is the intensity unit versus wave number. This is the sample reference beam, that is without the sample, only the moving mirror, etc., and this is with the sample. So, when these two are ratioed, what we get is the infrared absorption spectrometer. This is transmittance, left side is transmittance and right side is the absorption spectrometer. Usually this absorption spectrometer also can be taken care of by the FTIR. So, this is how the FTIR spectrum looks like. This is wave number versus absorbance. Normally we plot transmittance versus absorbance, because the quantity of absorbance will be very less. So, 100% transmittance, any aberration in the transmittance is normally recorded. Okay. So, this picture slide also I had shown you, that is as the mirror moves away by 1/4 lambda 1 by 2 lambda etc., and cosine this thing I had shown you, and I had explained to you the how the Fourier transform functions. And this is the interferogram which I did not draw it nicely in the yesterday's class, but anyway it does not matter. Now I have shown you the actual interferogram of a particular spectra, particular compound. Okay. And then the ideal spectrograph interferogram has a unique center burst which is corresponding to maximum intensity. Now I had explained to you a little more about the frequency resolution and the purity of the spectrum. Okay. Now I had also explained to you that Fourier transform series is an infinite series. So we cannot apply it directly to a system which is a finite system, because in our interferogram we make the mirror move only 1 centimeter or 2 centimeters. So it cannot be an infinite, even though the steps can be infinite, steps of increase can be infinite, but the IR spectrum we cannot sample infinitely, otherwise the spectrum will never be completed. So we have to truncate the series to some extent. That I had shown you here. This is known as apodization. This is also done mathematically with a computer program incorporated in the instrument itself, microprocessor, and two general apodizing functions are there, that is basically a weighting function or correction factor we have to apply. So Hanning and Hap-Genzel names these are the names of the apodizing functions based on the authors of the algorithms, and when we apply this, the noise also reduces to a considerable extent. So the signal produced is also a phase dependent phenomena, that is optical components of course still can cause a little bit of dispersion, and beam splitter also can cause, and then detector also can cause a little bit of disruption etc. Certain amount of optical aberration is always expected in all optical instruments. Okay, so you cannot have error free reflection, refraction and nothing like that. So the phase corrections are normally applied to reduce the photometric errors basically. So now I want to teach you about the sample handling. Here I had stopped yesterday, and regarding the sample handling, I have to tell you that infrared spectro instrumentation, even though it has reached a remarkable degree of standardization, the sample handling itself presents a number of problems. For example, there is no rugged window material for cuvettes, just like in spectrophotometry. We have quartz for ultraviolet and glass or polystyrene cells, cuvettes for visible range. Like that, if I want to take an IR spectrum from 4000 to 200 or 10 centimeters inverse, I do not have a single cuvette which can be transparent at all these wavelengths. So that itself is a big problem, because depending upon the area where you want to, region of infrared spectrum where you want to take the spectrum, I have to choose the cell material. Okay. That is one problem. And second problem is there is no universal cuvette. So we have to choose cuvettes for different areas of infrared. Among these, alkali halides such as sodium chloride are widely used, since they are transparent up to 625 centimeters inverse. That means from 4000 to 625 centimeters inverse, you can make a cuvette of sodium chloride crystal. So sodium chloride will not absorb IR radiation and you will get the spectrum. But the problem is, whenever you use sodium chloride, you cannot have a moisture in the sample, or the sample, you cannot take the IR spectrum of water, is it not? Because water will dissolve the cuvette. So, cuvettes will get deformed and then there will be a lot of errors and spectrum will not be pure at all. So, cell windows especially get fogged by exposure to moisture, because they are all made of sodium chloride crystals. So, fogging is a great problem. So, most of the IR sample compartments contain chemicals which will absorb moisture. Normally, we use silica or cobalt compounds for absorption of silica, water, moisture. So, not only that, when the cells do get fogged, they need frequent polishing. You have to remove that fogging by brushing, abrasion, and again after abrasion you need polishing to make the cuvette smooth. So, glass and quartz you cannot use in infrared because they absorb the IR radiation themselves. So, they are not ideal for neither for prisms, windows, etc., glasses, mirrors, you cannot use them, nor you can use them as the cuvettes. Okay. Now, almost invariably in all dispersive instruments, the sample compartment is positioned before the monochromator. In spectrophotometers and other areas, first we choose the wavelength and then put the sample compartment, so that the desired wavelength can be passed through the sample. But in infrared, first I pass the IR radiation totally through the infrared, totally all the infrared radiation through the sample, then go for wavelength selection. This is a one major difference between IR instrumentation and spectrophotometry, you can say. So, the compartment, sample compartment is positioned before the monochromator to conserve the IR energy, which is weak compared to UV and visible range, but also it will reduce the stray radiation, and optical aberrations also become less because all the IR radiation is falling on the infrared sample. Quite often we do use silver chloride as a window material. I think you are all familiar with silver chloride, because silver chloride is a precipitate generally obtained in the first group analysis of chemicals. All college, schools and high school experiments involve the precipitation of silver nitrate as a first group element using hydrochloric acid. So, any sample you take, dissolve it in water and then add a little bit of sodium chloride, you get precipitate. It means invariably that the sample contains mercury, silver or something like that. So, silver chloride quite a few people are familiar, and silver chloride is often used for moist samples, but it is not entirely satisfactory either. Quite often it is impossible to get a sample without moisture. So, what to do? So, sodium chloride cannot be used, but silver chloride can be used to some extent, but the problem is it easily deforms. Okay. So, it is so soft that it is deforms and it is not nice. Sometimes it is too soft. Silver chloride cells, cuvettes are not easy to handle because they are very soft. They may get pressed and then shape may change, and quite often there are several things that can happen. So, one has to be extra careful while putting the sample inside the silver chloride cells, cuvettes. And another problem with silver chloride is that it darkens on exposure to light. It is photosensitive. I think most of you are familiar with that, because silver chloride is one of the chemical that is used in photography. So, to get dark and white patches, you have to use silver chloride. So, silver chloride, once it darkens, you cannot make it white again. So, unless you dissolve it and reprecipitate and things like that. So, for frequencies under 600 centimeters, we can use those you cannot use both silver chloride and sodium chloride, but we can use a polyethylene cell, that is useful. So, characteristics of other useful window materials I am going to show you in the next slide. That is, so here I am plotting the IR transmitting materials. On the left side I have window material, on the right side I have the useful frequency, in which range they are effective. So, here sodium chloride, it starts from 40,000 to 625 centimeters inverse, okay. And then potassium bromide is good, that is up to 400 centimeters inverse, it is better than sodium chloride. Silver chloride approximately same range, but you cannot use it, it is not as versatile as sodium chloride, because its range is only 25,000 to 435. Silver bromide, essentially same thing, but it extends the range of the lower range up to 286 centimeters inverse. Below that they become non-transparent, they absorb the radiation. Other materials are calcium fluoride, not very good, but I do have calcium fluoride, works from 6000 to 1110 centimeters inverse. That means many bending vibrations, if you want to see, you cannot use them, is it not? So, in bending vibrations 1110 is the last vibration that can be shown, but many bending vibrations do occur around less than around 800, 700 like that. Barium fluoride is another one, quite good, but not very popular. Cesium bromide up to 270, zinc selenium is good up to 55 centimeters inverse, that is almost into the far IR range, but the problem is it is a vacuum deposited cell. So, in vacuum deposited cells, normally what happens is the deposit wears off after some time, by frequent handling, etc. The quality of the deposit goes down. So, it is not very ideal, but people do use them for accurate work. And polyethylene of course is quite good, from 625 to 33 centimeters inverse. So, with this information, what I have to tell you is sodium chloride is best, and then you can go to polyethylene, you can use both cells. So, you can use them in combination or alternately, one can go for that. Others also are useful depending upon the particular area of research in which you may be interested, area of IR, for example frequencies. Okay. So, how do I do the gas analysis in IR? Initially I had told you in my first class in this course that infrared analysis can be done on this glass, gases, solids and liquids. So, gases, how do we scan? Oh, it is very simple. I have to just pass the gas in the sample compartment, it fills the whole gas and the whole sample compartment is available for passing the IR radiation. So, whatever is the part of it is absorbed and then it is simple. Or I can use a 10 centimeter cuvette, a gas cell, something like this. this is the gas in and this is the gas out. You can seal them, and then these are the windows, sodium chloride windows or whatever, these two windows, sodium chloride windows, and then you can insert this into sample compartment. So, gases can be used, this can be 10 centimeter. So, gases can be very easily measured. I can use even I can use a small capillary tube like this with about 1 mm dia. You can use those small cylindrical things like what I showed you in my last slide, but you can also use a simple tube, and at the end of the tubes you seal them with sodium chloride window, and then the length of the tube you can even make it in meters, but roll them inside. So, the infrared radiation will pass through 1.5 to 120 meters also, but diameter will be very small. So, the quantity of the gas held within the cell will be much less. So, such cells are constructed with folded light paths also and gold surfaced mirrors. They are all special equipments used in petrochemical industries, okay, online. So, if it is a normal laboratory gas analysis etc., you use a 10 centimeter cell like what I have shown you here in my previous slide. Okay, that is very simple. Okay. So, this is the kind of gas silicon. So, then how do you do liquid samples? Liquid samples are usually scanned in their neat form or in solution. You can take the liquid directly in the on a sodium chloride cell. So, basically sodium chloride cell means it is a small plate of sodium chloride on which a drop of liquid is put, and then I put one more sodium chloride plate and then seal it on both sides, on the 4 sides with screws. So, that is the normal window cuvette. Okay. So, I can use that kind of thing, put a drop of take one plate, put a drop of the liquid, put one more cell. So, the liquid will spread all over the cell. So, that is also possible for that is known as neat form. If it is any liquid, we say take it neat, infrared spectrum, that means directly as solution. Sometimes if it is solid, you can dissolve it in a liquid and take it in the neat form in a solvent. So, in that case the solvent, if it has IR spectrum, you have to subtract it from the actual IR spectrum, because IR spectrum cannot differentiate between the sample and solvent. So, the sample thickness in between the two plates, when I put it here with one drop, the sample thickness becomes very small. So, that could be from about 0.001 to 0.05 mm thickness, but that provides you enough transmittance from about 15 to 70 centimeters inverse. That is quite normal. So, that much I wanted to tell you about these things. Now, we will discuss about the solids. So, what do we do with solids? One thing is we can discuss solids as a solution. I can make a solution of 10% carbon tetrachloride, because this carbon tetrachloride is a symmetrical element, no dipole moment. So, it becomes it has no IR spectrum except so 10% carbon tetrachloride, if the sample is soluble, you take a dissolve it in the liquid carbon tetrachloride, and from 4000 to 1333 centimeters inverse range, you can take the IR spectrum. Suppose you do not have carbon tetrachloride, then what do? We can go for carbon disulfide. That also does not have dipole moment, and it can be used in this range, okay, 13,333 to 650 centimeters inverse, we do not have any problem. Similarly, I can go for methylene chloride, acetonitrile and acetone. These are all other useful solvents. So, normally IR cells are constructed with sealed windows, which I had already explained to you, and the sealed windows like in sodium chloride windows, the edges must also be sealed. For that we need gaskets, so the liquid does not ooze out. So, these gaskets are made of copper or even lead, small thin lead strips to be put on one glass of sodium chloride. On that you put one more glass of sodium chloride and seal them with a little bit of pressure. You cannot use too much pressure because the sodium chloride cells may break. Once it breaks, it is to be thrown out only. They cannot be repaired. So, the lead gaskets and copper gaskets are usually wetted with mercury, so that it can expand and make a perfect seal between the two plates of sodium chloride. So, the whole assembly is again securely clamped in a stainless steel holder at the edge. So, it is a very nice engineering arrangement. You should go and see, if you get an opportunity, how the sample is handled in an IR instrument. Then as the mercury penetrates, the gasket it expands, producing a very tight seal. So, this is one way. And films, you can take the IR spectrum of the films also. Nowadays you come across lot of films in your day to day life, especially soaps and other things are all packed in thin films of plastics. Milk comes in plastic packets, and then your food, when you order in a hotel, it comes in a cling film. So, it should be food tolerant. So, like that there are several kinds of films which we use in our day to day life. Cellophane tape, many of them are useful, and the producers of those materials, they do use IR for quality control. So, for polymers, resins and amorphous solids, the sample is dissolved in a volatile solvent and you evaporate the solvent, you get a very thin film. Very simple technique. Simply dissolve it in a solvent, evaporate, and you get a very thin film. That film you can interpose in between the two plates and take the IR spectrum as usual. So, you can even place the solution on the sodium chloride window and you can seal it, that also will evaporate slowly. So, as the solvent evaporates, we get a very thin homogeneous film that is deposited, which can be scanned directly. So, for liquids and polymers, a drop of the solution may be placed and squeezed between the windows. You can press them a little bit to get a thin film, that is also possible. So, mulls. Now, I come to the solids, that is one way of taking IR spectrum is by taking making a solution. But suppose you do not want to make a solution, then how to take the IR spectrum? You can take the spectrum as a paste. How do you make a paste? You take a little bit of paraffin oil or even castor oil. Some paraffin oil is just like castor oil. So, you can take the sample in a bowl, put a drop of oil, put your solid and then make it a thin paste and scoop it a little bit with a metal spatula and smear it over the sodium chloride window, smear it and then seal it as usual and take the spectrum. Okay. So, the paraffin oil you can use, or it is also known as Nujol. So, if you order Nujol, they will not ask you why you are ordering Nujol or what is Nujol. Almost every chemical dealer knows what is Nujol and what it is used for. Nuzol is a high molecular weight liquid paraffin that is used for exclusively for infrared spectroscopy only. So, Nuzol has it is not that it is fully transparent, it has got specifically couple of peaks, but for the most of the part Nuzol does not have the it is transparent, it does not have absorption peaks IR. So, but Nuzol has peaks around 1330 to 2860 there is one peak, around 1460 centimeters inverse and 13 centimeter inverse. There are two peaks, the two peaks are so near each other that it looks like a single peak, single broad peak. I will show you some of the IR peaks in using Nuzol. So, actually no useful information can be obtained in these regions, okay, 1330 to 2860, 1462, 1374. You will not get any special information because Nuzol itself has got a peaks which is quite strong. So, any IR peak that is available in that range gets masked, it gets submerged in the Nuzol peak. So, if you are interested in those regions, better avoid Nuzol. Okay. So, another then what else you can use? You can use hexachlorobutadiene, that is another mulling agent, and it is also a liquid at room temperature. It has no carbon hydrogen bonds, hexachlorobutadiene, no hydrogen, carbon hydrogen. So, you can see all the sample, if it has got carbon hydrogen compounds, you can see all those peaks. So, a solid sample, another way of handling a solid sample is by mixing with potassium bromide. What we do is we take a bowl, you know, some marble bowl or something which is non-reacting, and I put a little bit of potassium chloride, potassium bromide, and then put your solid sample also, mix them nicely as if they do it in an Ayurvedic shop, mixing and powdering. So, when it becomes a very thin, nice uniform mixture, all you got to do is put it in a small cavity, press it and then press it, you will get a small 1 naya paisa size, still smaller 0.5 mm size disc containing potassium bromide and your sample. So, that you can use it directly into the IR sample compartment. Holders are there which can hold them, and such things are useful around 25,000 psi up to that is the pressure you have to apply to make a small disc of 10 mm diameter, that is 1 centimeter, and you can make it up to 2 mm thickness also. So, the IR radiation can pass through the disc, and then quantitative analysis also we can do by the pellet technique. Okay. So, I want to tell you so much about the infrared spectroscopy sample handling. Now, I will continue in my next session regarding the radiation sources. So, thank you very much.